Hello everyone, welcome to our channel. This is Dinesh MA, working as Assistant Professor in the Department of Electronics and Communication Engineering, Maharaja Institute of Technology, Mysore. In today's session, we will understand the applications of diode. One of the major applications of diodes is power supplies. Power supply has got various stages that consist of rectifiers, filters and regulators. Let us understand what are rectifiers, the different types of rectifiers. Rectifiers are basically the circuit that converts AC supply into pulsating DC supply. And we have majorly two types of rectifiers. One is half wave rectifier, the other one is full wave rectifier. Let us first understand the half wave rectifier. So, half wave rectifier is the one that converts either the positive half cycle or the negative half cycle of the AC power supply. And let us consider the circuit diagram for the half wave rectifier. So, first we will be having transformer, and let us consider a step down transformer here. So, this is primary coil. Let us say this is V1 and we have secondary coil across which we will be having the secondary voltage represented as V2. And here let us consider the diode connected like this, and further let us consider a load resistance RL. So, this is a circuit diagram what we have for the half wave rectifier. Now, let us understand the operation of this considering positive half cycle and negative half cycle individually. Now, considering positive half cycle, what we have is the diode's anode will be getting positive potential, whereas the cathode terminal will get the negative potential of the supply. So, because anode is connected to positive and cathode is connected to negative potential, the diode is said to be forward biased. So, when the diode is said to be forward biased, the diode will be working as a closed switch that allows the current to flow through the device. So, the current that is flowing through this diode flows through this resistance RL as IL that generates output voltage V0 across the load resistance. However, there will be voltage drop of Vf across the diode. So, what we understand here is during the positive half cycle, because diode works as closed switch, this allows the current to flow through the RL load resistance. So, that we call as load current, and this generates an output voltage V0 across RL. Now, coming to the negative half cycle, what happens here is the anode becomes negative with respect to cathode. So, when the diode becomes, the anode of diode gets negative potential with respect to cathode, the diode becomes reverse bias and it is said to be working as an open switch. So, when the diode is working as an open switch, it would offer high resistance path for the circuit current. So, there would be no current flowing through the diode and in turn through the load resistance RL. So, V0 is going to be 0 during negative half cycle, and the output voltage for positive half cycle and negative half cycle can be represented like this. Let us say VPO, which means peak output voltage, and this is given by VPI minus VF, where VPI is the peak input voltage and VF is the forward voltage drop across the diode. And VPI can be represented as 1.414 times of VI, where VI is the RMS input voltage, that is the primary voltage that has been fed. So this is the output voltage for positive half cycle, and the load current IL or the peak current, load current can also be called as the peak current, which can be written as VPO over RL. So where VPO is the peak output voltage and RL is the load resistance. Whereas during the negative half cycle, V0 will be equal to 0 because diode will not be conducting, so there would be no current that flows through the diode and in turn through RL. Because the current through RL is equal to 0, output voltage will also be equal to 0. Now let us write the input and output waveform for this half wave rectifier. So let us say this is the input voltage or the primary voltage V1 and this is the peak output voltage. So during positive half cycle, because the diode conducts, it allows the current to flow through the diode and in turn through load resistance RL, there will be an output voltage generated. So let us say there is an output voltage generated during positive half cycle of the input signal. This level is equal to or given by this particular equation. So what happens during the negative half cycle of the input signal? As I explained, as diode will not be conducting during the negative half cycle, there will be no current flowing through the diode and in turn through RL. So the current would be 0. Current would be 0 during the negative half cycle, and again when positive half cycle comes in, there will be a voltage generated across the load resistance RL. So this is the operation of the half wave rectifier. And in this circuit, because the diode is connected in this orientation, this circuit is called as positive half wave rectifier. Whereas if I change the direction of the diode, that is if cathode comes at this end and anode comes at this end, then the circuit is said to be negative half wave rectifier, where the output will be opposite to this. I mean to say, we will not be having positive half cycle in the output, rather we will be having negative half cycle coming at the output end. So this is all about the half wave rectifier. Now let's get into the second type of rectifier, that is full wave rectifier. In full wave rectifier we have two types. One is full wave rectifier with the center tap transformer, the other one is full wave bridge rectifier. First let us get into the full wave rectifier with the center tap transformer, and the circuit for this is as shown in this diagram. So here we can see the transformer we have used is of the type center tapped. On the secondary coil, we can see here there is a tap at the center of the coil. Because of this arrangement, we will be getting two secondary voltages. So in the circuit it is shown two secondary voltages, V2, the upper V2 and the lower V2. So these two are the secondary voltages what we have, and for these two secondary voltages we have two diodes, two semiconductor diodes D1 and D2 connected, and this is anode and this is cathode of D1, this is anode and this is cathode for D2, and here we have the load resistance RL connected between the cathode of D1 and the center tap of the secondary coil of the transformer. Now let us understand the operation of this circuit for positive half cycle and negative half cycle. Now during positive half cycle, so what happens here is, this is going to be plus and this is going to be minus. Same way, this is going to be plus and this is going to be minus. So obviously what happens here is, diode D1 will be forward biased and diode D2 will be reverse bias, because D2 anode is connected to negative potential with respect to cathode, whereas anode of D1 is connected to positive potential with respect to cathode. Diode D1 will be forward bias. So during positive half cycle, let us put up the equivalent circuit diagram. So the circuit looks like this. So because diode D1 is forward biased, it will be working as closed switch. So let us show it like this. This is diode D1. And diode D2 will be working as open switch. So this is diode D2, because of this arrangement, the current is allowed to pass through diode D1 and the same current will be flowing through the load resistance RL, where it generates the output voltage V0, and here when it comes to this, so it flows back like this and back like this. So here we can see a closed path for the current to flow through the upper secondary coil, diode D1 and load resistance RL. So during positive half cycle, through diode D1 and load resistance RL, there will be current flowing which generates an output voltage V0. Now coming to the negative half cycle, during negative half cycle, the polarity changes. So what happens here is, this becomes minus and this becomes plus and this becomes minus and this becomes plus. So what is happening here, diode D2 is getting forward biased and diode D1 is getting reverse biased. So let us put up the equivalent diagram for this. So the circuit looks like this. So this is the secondary coil. Let us get the center tap out of the secondary coil, and diode D1 is reverse bias, so it will be represented as open switch, and here we have the load resistance connected, and diode D2 will be working as closed switch because it is been forward biased. So let us represent D2 like this, and here we have the connection like this. right? So this is the equivalent diagram for negative half cycle. This is minus plus minus plus. So diode D1 is working as open switch, diode D2 is working as closed switch. So now the current will be flowing in this direction through D2, right? And then it moves up like this. So comes to this point and flows in this way. So let us call this as IL and this is RL. So because the IL is flowing in this direction, output voltage V0 with these polarities will be generated and the current comes back in this direction. So here we have a loop like this. So the current during negative half cycle is flowing through diode D2 and through RL in the same direction as with the positive half cycle. So the polarities of V0 will be same in both the half cycles. So the output voltage can be written like this. During positive half cycle, this is the output voltage generated. This is because of diode D1. And during negative half cycle, this is the output voltage generated and this is because of diode D2, and this keeps on repeating. So what we can see here is during both positive half cycle and negative half cycle, because of diodes D1 and D2, the current flows through the load resistance RL. So because both the cycles the output voltage is generated, this rectifier is called as full wave rectifier. Now let us get into the operation of full wave bridge rectifier. Before getting into the circuit operation, the earlier rectifier, that is the 2-diode full wave rectifier or the full wave rectifier using center tap transformer, has an disadvantage. Because of the center tap transformer what we have used, because we have two secondary voltages, when a particular diode is reverse biased, the algebraic sum of two secondary voltages will be applied across the reverse biased diode. So this is the problem associated with the 2-diode full wave rectifier. So we have the other circuit, that is full wave bridge rectifier. So here you can see we have the regular step down transformer with other arrangement of the diodes. So we have 4 diodes connected as a bridge here, D1, D2, D3 and D4. In between we have the load resistance RL connected, across which the output voltage V0 is generated. Let us understand the operation of this for positive half cycle and negative half cycle. Now during positive half cycle, what we have is this point is going to be made positive with respect to this node. So this makes diode D1 and D2 forward biased, whereas diodes D3 and D4 will be reverse biased. So have a look at this. This is anode and this is cathode. So anode of diode D1 is positive with respect to cathode, whereas this is cathode terminal of D3. So D3's cathode has become positive. So D3 is reverse biased here. In the same way, the cathode terminal of D2 has got the negative potential with respect to anode terminal. So D2 is also forward biased along with D1. Same way here, the anode of D4 is getting negative potential with respect to cathode. So D4 along with D3 gets reverse biased. So D1 and D2 will be forward biased, D3 and D4 will be reverse biased. So D1, D2 works as closed switches, D3 and D4 works as open switches. So let us write the equivalent diagram for this condition. So during positive half cycle, this is how the circuit looks like. So here we have D3 which works as open switch. here we have D4, where D4 works as open switch. This is D3 and this is D4. And here we have D1, where D1 works as closed switch, and here in this path we have D2. D2 also works as closed switch, and this is RL. And because of this arrangement, now the current is flowing in this direction, so comes through D1, comes to this point. So where we have 2 points here, 2 paths. So this path is closed path, this path is open path, so current cannot flow through this path. So current flows in this path, generating the output voltage across RL. And when current comes to this particular node, again here we have 2 paths. This is open path, this is the closed path. So current flows through D2 like this. Again when it comes to this particular node, so this is open path, this is closed path. So current will be flowing in this way, flowing back in this way. So makes a closed path for the current. So during positive half cycle, current flows through D1, RL, D2 back to the same point, making the closed path, generating the output voltage V0. Now considering the negative half cycle, so this becomes minus and this becomes plus. So what happens? The cathode of D2 gets positive potential, so D2 gets reverse biased. Anode of D1 gets negative potential, so D1 also reverse bias. So D1 and D2 will be working as open switches, whereas the negative potential is connected to cathode of D3, so D3 working as closed switch. At the same point, the positive potential is applied to anode of D4, so D4 will also be working as closed switch because of the forward bias condition. So let us put up the equivalent diagram during negative half cycle. Right, so this is secondary voltage what we have. This is RL, and here what we can see is the path of D3 which works as closed switch, and this is path of D4 again which works as closed switch, whereas this is the path of D2 which works as open switch. This is the path of D1 again which works as open switch. So now because of this arrangement, current will be flowing in this direction. When it comes to this particular node, so again 2 paths we have, this is open path, this is closed path. So current flows like this through D4 and comes to this particular node. So here again once again 2 paths, this is open path, this is closed path. So current flows through RL, generating output voltage V0, and when it comes to this particular node, so again this is closed path, this is open path, so current flows like this through D3. So come to this particular point, so again this is closed path, sorry, this is open path and this is closed path. So current flows like this and comes back to its origin. So during negative half cycle, what we are seeing here is the current is flowing through D4, through RL to D3 back to its origin. So output voltage V0 is generated with the same polarity as with the positive half cycle case. Right? So what we can understand from this is in both the positive half cycle and negative half cycle, the output voltage V0 is generated with same polarity. So output waveform can be written like this. So here this is because of D1 and D2, here this is because of D3 and D4, and again the cycle repeats. So this is the operation of full wave bridge rectifier. So in this session we have understood the operation of three circuits. One is the half wave rectifier, where we discussed both the positive half wave rectifier and the negative half wave rectifier, and then the second one is the 2 diode full wave rectifier or full wave rectifier with the center tap transformer, and the third one is full wave bridge rectifier. So that's all what we have for this session. In the next session we'll understand the filtering operation required in the power supplies. Thank you. In this session we'll understand the filters and regulators. There are different types of filters available. We shall consider the capacitor filter for our discussion. Here you can see the circuit diagram for a full wave rectifier with capacitor filter. This forms the bridge circuit. In the previous session we had seen a circuit where the bridge arrangement was looking different than this. This is also considered to be bridge arrangement. So D1, D2, D3, D4 forms the bridge circuit, and we supply AC signal for this, and here we will be getting the pulsating DC output after this particular point. And the pulsating DC will be fed as input to this capacitor. So this capacitor C will be working as the filter circuit, which is connected across this load resistance RL. In fact, we can interchange the positions because these two are connected in shunt paths. And now here you can see the pulsating DC, which is fed as input for the filtering circuit. Now when there is a pulsating DC coming in, what happens with the capacitor is, we know one of the properties of the capacitors is charging and discharging. And that is how the capacitor will be working as a filter in this circuit. Now let us get into the waveforms to understand this operation well. Now let us say the pulsating DC, which looks like here white in color, and this will be supplied to capacitor to charge the capacitor. And capacitor, let us say it starts charging to its peak. Initially of course we will be having in the initial cycle right from 0. So the capacitor charges to its peak, and once it charges to its peak it starts discharging. So discharging happens like this. So slowly the capacitor starts discharging. Then once again when there is a pulsating signal comes in, the capacitor again starts charging. So it starts from this particular point and it reaches to its peak, then again it starts discharging like this. So if you look at this particular thing, this segment, so what we can see here is, earlier with the rectifier the peak to peak variation was from 0 to the peak output voltage, but now with the help of capacitor we have reduced the peak to peak voltage. Ignoring the first cycle, what we have is the peak to peak voltage, now it has been reduced to this limit. So this is V gamma peak to peak. So this is going to be considered as the output of the filter circuit. So rectifiers has the output which has huge variation in its output, whereas employing capacitor will bring down this variation. So we say the ripple, the variations in the output has been reduced. So this we are doing in attempt of getting a DC output which is a straight line. So with the help of the capacitor, the variation has been reduced. Now how do we decide the value of the capacitor? The value of the capacitor C is given by IL. so where IL is the load current and T1 divided by V gamma. So C is the capacitor, IL is the load current that is charging the capacitor, T1 is the discharging period. So from this point to this particular point. So this time duration will considered as T1. So capacitor C is given by IL into T1 divided by V gamma. So where V gamma is the peak to peak voltage. So this is how we can reduce the ripple content from the rectified output using a capacitor filter. Now further the ripple can be reduced by employing another capacitor across the same path. So as many number of capacitors we have, so filtering happens smoothly. So we'll be getting less ripple, less variations we'll be having in the output voltage. So this is all about the operation of capacitor filter. Now let us understand the regulators. Zener diodes are the main component used in regulator circuit. So let us understand the Zener diode before getting into the concept of Zener used as a regulator. Now the Zener diode is represented like this. This is the symbol of Zener diode. This is said to be anode and this is said to be cathode. So Zener diode will be employed in the reverse biased mode in the regulator circuits. So let us understand the reverse characteristics of the Zener diode. So the reverse characteristics of Zener diode look similar to the reverse characteristics of any PN junction diode. So let us draw the reverse characteristics of the diode. So this is the third quadrant what we have, and the x-axis represents the voltage. So this is reverse voltage, and the y-axis represents the current in milliamperes, and this represents the reverse current IR. So the reverse characteristics of a Zener diode looks like this. So as it was with the PN junction diode, so here too there will be a small, very small leakage current that flows in the reverse bias mode. And here we have a couple of parameters which are important with respect to Zener diode to be noted. So what are these? Very first one, the first parameter is Zener breakdown, which is represented as Vz. The very first parameter is Zener breakdown, which is represented as Vz. So Zener breakdown is the reverse voltage at which the Zener diode enters the breakdown region. So in this diagram, this point is the Vz point. So minus 6 volts is the Zener voltage, Zener breakdown voltage. So when the diode enters this breakdown region, there will be a constant voltage maintained across the diode, what we call as Zener voltage. And the second parameter is minimum Zener current. Minimum Zener current, which is represented as IZK. Now coming to this graph, IZK is the reverse current that is read at the knee of the reverse characteristics. So at this particular point, what is the current? So that shall be read as IZK. So IZK is the reverse current read at the knee of the reverse characteristics of the Zener, and this is the minimum current that is required to maintain the breakdown region. If you go less than this, then Zener will not be working in the Zener breakdown region. So we should make sure that the circuit elements will allow a minimum current of IZK at least, so that the Zener will be working in the breakdown region. And the third parameter is maximum Zener current. This is represented as IZM. So this is the reverse current again that the Zener can carry maximum without destroying, or this is the maximum current in the reverse direction what the Zener diode can carry without exceeding the maximum dissipation, maximum power dissipation. So usually this is the level minus 40 milliamperes is the point, so what we consider as IZM. Right, and the fourth parameter is maximum power dissipation. Maximum power dissipation, and we represent this as PD, maximum power dissipation. So this is the maximum power what the Zener diode can handle without destruction. So this is called as maximum power dissipation, and this parameter PD is given by Vz into IZM, whereas Vz is the Zener breakdown voltage or the Zener voltage, and IZM is the maximum Zener current. So these are the parameters associated with any Zener diode. Now keeping these parameters in mind, we'll use any Zener diode to work as a regulator. So now let us understand how a Zener diode can be used as a regulator. So here we have two conditions. Condition number one is when there is load connected, and condition number two is when there is no load connected. So Zener diode will be analyzed as a voltage regulator under two conditions. One is no load condition and second one is loaded condition. So we'll understand these two conditions and see what are the differences between these two. So let us get into Zener diode as voltage regulator in two different conditions, that is as mentioned with load and without load. So first let us consider without load condition. Let us say like there is a voltage source . Let us call this as ES, and let us consider a Zener diode across this. And here we have a series resistance, and let us say this is RS, and here we have a Zener diode connected like this. So make sure that the Zener diode is connected in reverse bias mode. Let us say this is anode and this is cathode, and let current IS be the input current that is flowing in the circuit, and here we have a voltage across the Zener, what we call as Vz, and let us apply KVL, Kirchhoff's voltage law, through this path, so that ES is equal to Is into Rs minus Vz. So Rs is equal to Es minus Vz divided by Is. Now, because this is the only current that is flowing through the circuit through the Zener diode, this can also be represented as Iz. So, this equation can also be written as Es minus Vz divided by Iz. Or this equation can also be written as Iz is equal to Es minus Vz divided by Rs. Now, the point to be noted here is the series resistance Rs should be selected in such a way that the Iz, the current Iz will not go lesser than Izk, that is minimum Zener current, and will not be higher than, at the same time will not be higher than the maximum Zener current Izm. So, the Rs value should be selected in such a way that Izk should be less than Iz and Iz should be less than Izm. So, this is the design constraint we have in this particular circuit. Now, coming to the Zener diode as voltage regulator with loaded condition. So, let us look into the circuit diagram for this. So, let this be Rs, and here we have a Zener diode connected. So, this is Es, this is Rs, and here comes the circuit current Is. Now, we need to consider a load. So, let us connect a load across the Zener. So, let us say this is RL. Now, look at this. So, Is is the input current that is flowing through the circuit, and when it comes to this particular node, it will be splitted into two currents. One shall be called as Iz, the other shall be called as IL. So, the current that is flowing through Zener shall be called as Zener current Iz. The current that is flowing through load resistance shall be called as load current IL, right? And here we have the output voltage V0, or this can also be called as Vz. So, now Is can be written as Iz plus IL, right? And Vz just like this. So, by applying KVL, we can write the expression for the value if I want to determine what is Iz, or if I want to determine Vz, or if I want to determine IL. So, we can apply KVL and find out the values. So from the circuit, we can write Is is equal to Iz plus IL. Let us call this as equation 1, and Is can also be written using KVL. Is can also be written as Es minus Vz divided by the series resistance Rs let this be equation 2. By equating these two equations, I can write Iz plus IL is equal to ES minus VZ divided by RS. And we know that here this is the input current which should be limited by the maximum Zener current, right? So I can also write Is is equal to Izm. So Izm can also be written as Iz plus IL. So now this is the maximum current that should be allowed through the circuit, so which can be controlled by using the resistance Rs. And if this is the maximum current and which is written as Iz plus IL, so considering this Iz and IL that is flowing through Zener and RL. So let us say, like for example, if the load gets maximum current, considering if RL is minimum, load will be getting the maximum current, then Zener will be getting the minimum current. Then Izm can be written as Iz min plus IL max. Izm can be written as Iz min plus IL max. So in this condition, this Iz min should not be less than Izk. So that is the design point what we have. So this Iz min should not be less than Izk. And the other case is Izm can also be written as Iz max plus IL min. So if the load current is going to be minimum, so when the load current is going to be minimum, if RL value is selected as maximum value allowed, then the load current is going to be minimum. If it is too high, then IL min is going to be 0, then all the current will be flowing through Zener, that is Iz max, and this Iz max should not be more than this Izm. If not, the diode is going to be blown off. So this is the design constraint what we have. So we have a load resistance RL using which the Zener current can be controlled. The current that is allowed to pass through the Zener diode can be controlled. So this is the working of a Zener diode as a voltage regulator under no load condition and under loaded condition. So in this session we have understood the operation of capacitor filter and the regulator, where we used Zener diode as the regulator, and that's all what we have for this session. Thank you.